Hey everyone, and welcome back to our next video. This one's looking at the structure of matter. We're going to go deeper from where we have been. Previously, we've been talking about the kinetic theory of matter, and we've mentioned that matter is made up of units called atoms, but we haven't really dug deep into that. That's really what this next series of videos is going to do, is kind of look at the structure of matter, look at what the atoms are, how they're arranged, these sorts of things. So just a reminder, matter is anything that has mass and takes up space or has volume. So mass and volume are the two big defining factors when we're looking at matter of any shape or size, whether we're talking about a mountain or an atom. We're going to be looking for those two qualifiers. So, of course, matter itself is made up of atoms, tiny little jiggling particles that exist far beyond the ability of our microscopes to see. These atoms are in constant motion, which is very important. The degree of that movement, that motion, really determines what phase the matter is in. So, the atom is made up of several parts. Here we have an example of a carbon atom. So inside we see protons. Now protons in this particular photo are blue positives. You'll often see in representations of atomic structures that protons will have some sort of plus going on with them. Sometimes we'll say P, sometimes we'll say P positives, sometimes we'll, have blue positive spheres. Generally, that's very important because it denotes the charge of the proton. We also have neutrons. Those would be the orange spheres that don't have a charge inside the nucleus with the protons. And circling around that are the electrons, the tinier negative signs. So with the electrons, we both show in this particular image the relative size of the subatomic particles, as well as the negative charge that exists on the electrons. So if we took a deeper dive into it, the protons themselves are positively charged particles, and those positively charged particles help make up the nucleus of the atom. So in this case, we have 3 protons in the nucleus. We also have 4 neutrons for a grand total of 7 things within the nucleus. Now, because this has 3 protons, I know that it's lithium. Every atom that has a set of protons that is 3 would be lithium. The protons define the atom to a large extent. They're probably the most important piece when you're trying to identify what atom you're looking at, is to look at the protons first. That's going to tell you which of the elements you're looking at. The protons are always equal to the atomic number of the atom. That's super important because a lot of times you're trying to figure out how many protons are in an atom. Sometimes you're trying to figure out what atom you're looking at based on the number of protons that you're given. So ultimately, the fact that protons equal the atomic number is kind of a huge deal. And finally, protons contribute to the mass of an atom. They're considered to be 1 atomic mass unit per proton. And we'll go into that more in a little bit. One final piece about protons is that they are equal to the number of electrons. So if you notice in this particular picture, we have 3 protons, 3 electrons, and 4 neutrons. So protons and electrons are always going to be equal, provided that you're looking at an atom and not an ion. Ions can actually have more or less electrons, and we'll talk about how that works in a little bit. Neutrons, on the other hand, they're neutral. Neutron, neutral. They have no electric charge. They live up in the nucleus, and they do contribute to the atomic mass, but there's no charge coming from a neutron. Electrons, on the other hand, don't live in the nucleus. They're these negatively charged particles that are around the outside of the nucleus. And we use a lot of terms to describe this. I'm trying to stick to orbits and levels, energy levels, this time around. Orbitals is another word that describes a slightly different mechanical model of how these work. It's a little more true, but a little more difficult to understand. So I'll try to stick with energy levels or orbits, but the electrons exist in these energy levels, and the energy levels themselves can only hold so many electrons. So the first energy level, the closest to the nucleus, can only actually house 2 electrons, and the next one out can actually hold 8. Okay, so it goes up quite a bit. And the next one out can actually hold up to 18, but it kind of starts dividing into multiple sublevels of that third energy level. So you could also look at it as just 8 from a certain perspective. That will probably go into a little bit when we talk about what's called the octet rule and why the noble gases are so stable. But for now, just understand that you go up in energy levels, and 2, 8, 8 is usually what we're going to work with the models we're going to be making. Ultimately, the electrons are moving around at a super crazy speed, and that rapid motion around the nucleus creates an electron cloud. So we often talk about the probability of where an electron is, especially in the model that looks at orbitals instead of orbits. But because they're moving super rapidly, we'll just describe it as an electron cloud around the nucleus. The important piece for the mass part is that electrons are super insignificant compared to the protons and the neutrons. It's serious several orders of magnitude in difference between the masses between them. So electrons aren't really counted when we're discussing the mass of an atom. And if the atom is neutral, then the number of electrons is equal to the number of protons. Again, there's these things called ions where the electrons you've gotten more electrons or less electrons that are very common. Table salt is an ion. So they happen all the time, but for right now, let's just focus on the electrons are equal to the protons until we get going. And ultimately, the electrons are the part of the atom that allows us to make chemical bonds. Chemical bonds are what we use in molecules. So you're going to need to know how many electrons there are, especially how many electrons are the farthest out. This creates a very special type of electron that we call the valence shell electron, or the valence electrons. The valence electrons are the ones that actually participate in bonding between atoms to form the molecules. So a hydrogen's valence electron bonds with an oxygen's valence electron. That creates a bond between those. And if you make 2 of those bonds, you would have H2O, or water. So the nucleus of an atom is where we've grouped together the protons and the neutrons. And actually, the nucleus is the protons and the neutrons, they're actually made up of smaller particles. And those particles are called quarks. We're not going to go too deep into that. You should know that they're made up of other things, other subatomic particles. But ultimately, that's a little bit beyond what we want to touch on in our class. But for the most part, all the protons and neutrons are going to be contained within this nucleus where they're hanging out in the center of the atom. That's the important piece to know. The electron cloud has these different energy levels, okay? And ultimately, the energy clouds are these crazy three-dimensional shapes, spheres and dumbbells and like this flower shape and stuff that are really cool. But for simplicity's sake, we're going to use what's called the Bohr model. And the Bohr model didn't visualize just how crazy reality really is. It was more of a simplistic electrons are cruising around in an orbit, almost like a planet around the sun. And that sort of model is a lot easier to get our heads around than, oh, it's these crazy shapes, which it actually is. So we're just going to focus on going around in circles right now, okay? And that's really going to be where we're going to keep it for our class. The orbits closest to the nucleus are the lowest energy orbits, and those are the ones that are most desirable. You want to be next to the nucleus if you're an electron, okay? That is super desirable, and you want to hang out there. Those are the lowest energy states. The electrons want to be in as low an energy state as possible, and basically nature keeps messing with their ability to be at the lowest state, and that's kind of what chemistry is about. Okay, so if we were to start digging into some of these, the hydrogen atom's, of course, the simplest of all atoms. And there's a single electron in the first orbit. There's a single proton. It's very simplistic to draw this. And we're going to go into drawing these in the next video in the series. But for right now, just take a look at a few of these and what they kind of look like. Oxygen jumped up quite a bit. The first orbit's now full on oxygen. The first orbit caps at 2 electrons. And then I have 6 more, and those 6 more go into the second orbit around the first. Okay, so I put 2 electrons right next to the nucleus. I put them inside that first orbit because that's the most desirable place. And then the next 6 end up in the next orbit up, the second energy level. You notice that the nucleus gets pretty crowded if you're trying to draw all the positives and the neutrons. It gets a little crazy in there. So we have some ways to make that a little simpler. And the sodium atoms, I mean, this is just 11 protons with 12 neutrons, and look at how crazy you've gotten inside that nucleus already. And at this point, we've actually moved up to a third orbit because the second one filled up with its 8 electrons. So we have 2 electrons in the first orbit, 8 electrons in the second orbit, and 1 electron hanging out in the outermost orbit. Now that outermost orbit is going to be the valence electron, okay? Valence electrons would have happened in oxygen and hydrogen as well. The outermost electron is the valence electrons. So in the case of hydrogen, the 1 electron that it has is its valence electron. Whereas with oxygen, you had those 6 that were hanging out in the second orbit that would ultimately be the valence electrons for a oxygen atom. And again, we're going to work on making these drawings on our next video, so don't worry too much about how you get here yet. We're going to go through that step by step. So ultimately, we've got protons, neutrons, and electrons all hanging out, making up this atom. And if you look at their masses, we got neutrons and protons at 1.67 times 10 to the negative 27th kilograms. So very tiny. I mean, this is an atom that we're talking about. There's so many atoms inside a drop of water. It's really crazy. And the electron itself is 9.1 times 10 to the negative 31 kilograms. So let's think about what that actually means in terms of masses. So if I was looking at an electron to a neutron, there's 1,839 electrons for every neutron. 1,839 is an order of magnitude of 4 in difference between a neutron, 1 neutron, and electrons, okay? And the same thing's going on with protons. 1,836 electrons is the mass of a proton. So ultimately, what you can conclude from that is a neutron is pretty much the same as a proton as far as mass goes, while the electrons really don't contribute at all to the mass. They're down in the thousandths place of the decimal of the mass of the atom, so you're not going to actually pick that up very easily. The atomic number is the number of protons in the nucleus of an atom. So ultimately, that's giving me the definition of the atom. Okay, that's a very important part of the atomic symbols. And when you look at those, you usually see a number above. And that number is the atomic number and tells you exactly the number of protons that are going to exist in that nucleus. Okay. Every single lithium atom has 3 protons. There's no such thing as a lithium atom that has 4 protons or 1 proton. Okay, the protons identify the atom. If it has 1 proton, it's hydrogen. If it has 3 protons, it's lithium. 2 protons, it's helium. Always, always and forever. Now, atomic mass is made up of those protons and the neutrons added together. So the total number of protons and neutrons in the nucleus is the atomic mass. And that atomic mass is usually expressed in what's called atomic mass units. Every neutron and proton have 1 atomic mass unit, or AMU. So if I'm looking at this image here, I see a lithium atom. I know that because it's got 3 protons. The 4 neutrons in there are going to add together to give me an atomic mass of 7, which is roughly right, but we got to take into account that sometimes the neutrons aren't always the same. Now, what's holding these together is actually the 4 forces of nature. One of them is not really represented too well in this case, and that would be gravity. But the electromagnetic force, the strong force, and the weak force are all very much present within the atoms. Gravity, we have a picture here of, you can almost think of it as one large mass like a planet and a much smaller mass like a moon, or even a sun and a planet orbiting each other. Ultimately, gravity here is a force of attraction between 2 objects that's caused by their masses. The amount of gravity between 2 objects is going to depend upon their mass and the distance between them. Now, if you think in terms of the gravity that a star could exert, because it's got so much mass, that's going to be massive compared to something like when you're talking on the scale of atoms, where those masses were in -27th, 10 to the -27th kilograms. That is not exactly supermassive. There would be some attraction due to gravity, but not much within the atom itself. Electromagnetism, on the other hand, plays a huge role. Electromagnetism is going to play a role because we have charges of positive on the protons, we have negative electrons, okay? And those are going to both attract each other and repel each other. So the electrons aren't going to want to hang out with the electrons, hence all these energy levels. And the protons aren't necessarily going to want to hang out with the other protons inside the nucleus. So there's got to be some other massive force going on that's allowing them to hang out together. And that particular force is called the strong force. The strong force is the force that holds the atomic nucleus together. And it's actually so powerful, it's such a huge scale, that the strong force is able to override the repulsion that's coming from the electromagnetism. So the strong force is actually a greater force than electricity. Okay? There's one other force that's going on inside the atoms, and that is the weak force. The weak nuclear force actually is a little more subtle, and it plays a key role in the ability of particles to decay. So you may have heard of radioactive decay, things like nuclear weapons, stuff like that. Ultimately, that is coming in due to the weak force interactions that are also happening on the nucleus. So 4 forces of nature Electromagnetism, the strong force, and weak force playing huge roles, gravity playing a small role, all in holding these atoms together. Now, I mentioned previously that the atomic masses aren't necessarily even. Atoms that have the same number of protons but a different number of neutrons are called isotopes. Okay, some of those isotopes aren't stable and they actually will undergo radioactive decay. So let's look at hydrogen, for instance. Hydrogen's our simplest atom. We have one proton, one electron. That's the normal, standard, out your box hydrogen. Okay, we can also call this protium, proton, giving it its name. But there is also a small amount of hydrogen that has one neutron, very small amount, and that's actually called deuterium. Deuterium has one proton and one neutron. The one electron stays the same, okay? But there's actually even a third type, tritium. Tritium is a hydrogen that has two neutrons and one proton. And at this point, it actually becomes unstable. So that's where you would actually see those weak force interactions because hydrogen in the form of tritium would eventually decay into other things. Now, these isotopes come into play and they give us the full atomic mass. Okay, so the atomic mass of an atom is actually the weighted average of all the masses of the naturally occurring isotopes. The average ultimately considers the abundance within nature of each of the isotopes. So, for instance, if we're looking at hydrogen, uh, protium is going to be much more abundant than deuterium or tritium would be. You can find all these on the periodic tables, but ultimately you would take the atomic mass of protium, deuterium, and tritium and use their abundances to calculate those numbers, which is why the numbers are never going to be nice and even. They're always going to be some weird decimal when you look at the atomic masses. Ultimately, for drawing structures, which we're going to talk about next time, you would want to round to the nearest whole number, and then you can actually figure out the number of neutrons and like the most common of the isotopes. But we'll discuss isotopes more and how to get all the structures on the next video. We've probably gone way too long for today. So thanks for your attention and have a great one. Bye.